Okay. In the last lecture, we looked at the definition of inertia subgroup, wild inertia subgroup, and we proved that the quotient of inertia subgroup by wild inertia subgroup is a cyclic group of order dividing norm of p minus 1. And I told you that you can study wild inertia subgroup by defining higher ramification subgroups, but we are not going to pursue that course here. Instead, today what we are going to do is we are going to relate ideals with Galois groups or elements in Galois group using these notions of decomposition subgroups, etc., that we have defined. And even though it might all seem very formal in the way we do it and quite natural in the way we are going to do it today, you should realize that this is very deep, because we are relating ideals, which is a completely arithmetic thing, numbers in a number field, with elements of the Galois group, which is a very algebraic thing. And historically it took quite a long time for people to define this map. So, a lot of these objects that we have studied were all defined in the 19th century, and people even came up with statements of class field theory and even proofs of class field theory without defining this map that we are going to define today. And so, it's quite remarkable that they could do all this without defining this map, and it was down to Emil Artin who defined this map early in the 20th century. So, this is called Artin reciprocity map. So, you should really sort of keep in mind that what we are doing today is extremely deep and extremely non-trivial, although by now it kind of the way the theory is developed, it all seems very natural. So, recall that GP is decomposition subgroup and there is a homomorphism from GP to Galois group of Kp over Kp with kernel I sub p. Okay. And we saw that order of I sub p is equal to E. Okay. So, if E is equal to 1, in other words, if P is unramified in K over F, then IP is trivial, and we have an isomorphism of groups which is given by GP to Galois group of Kp over K sub p. This will turn out to be an isomorphism. Later on, we will show that only finitely many prime ideals in F ramify in K over F. So, if you take a finite extension K over F of number fields, then only finitely many primes in F will ramify in K. So, whatever I am going to say now about unramified primes applies to almost all primes of f. Okay. So, it applies to all but finitely many primes. So, although it seems like we are putting a very restrictive condition on primes that they do not ramify to say what we are going to say in today's lecture, it actually applies to all but finitely many primes. Of course, those finitely many primes that ramify are also important, but for the things that we are going to do today, it is we can concentrate only on unramified primes, and that is usually enough for most things that we want to do. Okay, so, so let us say, so now P is unramified in K over F, then we can define. So, irrespective of this, there is so Galois group of, for this statement about finite fields of course does not require P to be unramified, but Galois group, this is cyclic, generated, and it is not just cyclic, it has a canonical generator generated by the Frobenius element. It is actually a bit awkward to call it the Frobenius element because there are two choices, but since we are doing arithmetic, I will choose the arithmetic Frobenius, and there is something called geometric Frobenius. By the Frobenius element, which is sending x to x to the power norm of P. So, this whenever I do not write subscript for norm, it means norm from that field down to Q. Okay. So, this is called the Frobenius element, right. So, you may have seen the usual Frobenius when k sub small p is z mod pz. In that case, the Frobenius will be x going to x to the p, but this is slightly more general version of it. Okay. So, this is the Frobenius element, which I will denote as sigma sub, so denoted sigma sub p in Galois group of Kp over Kp, okay. Or maybe it is more accurate to denote it with capital P, right, okay. Does not matter really because I am not going to use that notation much. So, if P is unramified in K over F, then G sub P is isomorphic to Galois group of Kp over K small p, okay. And we denote the unique element in G sub p mapping to sigma p in Galois group of Kp over K small p by K over F over P. This is called the Frobenius element, okay, again called the Frobenius element, okay. We can of course do this slightly more generally even if P is unramified. In this case we lose uniqueness, right. So, remark, if P is not unramified, so it is ramified in K over F, then we may define K over F over P to be any element of Gp mapping to sigma p. right? We still have the map. It is not like this map is not there, it is just not an isomorphism. So, we can take this we can take a Frobenius element to be any element mapping to sigma p. Okay. So, it is not an element in GP anymore, it is an equivalence class of elements, or it is a coset of the inertia subgroup. Okay. So, there will be E different elements with this property. Okay. So, there are E different choices for K over F over P. So, we can work with this if we want to, but generally we will just work with unramified primes, and as I said, this is not a serious restriction because because all but finitely many primes will be unramified. So, here is maybe an exercise if you like. K over F sigma p, this is equal to sigma K over F over P sigma inverse for any sigma in G, which is Galois group of K over F. So, if you have understood decomposition subgroups and this map from decomposition subgroup to Galois group of residue field and how the action on the decomposition subgroup works, then you should be able to prove this very easily. Okay. By the way, so also so that is one part, and maybe the part before that which should have gone before that is the following: K over F P alpha is congruent to alpha to the norm of P modulo capital P for all alpha in OK. Okay, so that is also exercise if you like. Okay. So, what have we done? So, we can define, so you consider the set. So, we have defined a function from the set of all non-zero prime ideals P in F unramified in K over F to Galois group of K over F, and what is this map? It goes to this over P. Yeah, okay, maybe right, I mean this is not well defined, right. So, I will assume that K over F is abelian, then this is well defined, right. It does not depend on which capital P I choose in above small p, because they are all conjugates, and in abelian group conjugates means equal. Okay. So, you see this is remarkable because on the left hand side we just have prime ideals in the base field, whereas on the right hand side we have Galois group of a bigger extension. Okay. So, this is called Artin map. Okay. Of course, we can also extend it to non-zero ideals which are co-prime to prime ideals that ramify, or we can also extend it to non-zero fractional ideals which are co-prime to primes that are ramified in K over F, but those are just technicalities. The basic thing is this map, and a priori because there is no structure on the left hand side, it is just a set of prime ideals, this is just a function. Okay. If we extend it to all non-zero fractional ideals, then we know that that is a group and then in that case this becomes a group. Of course, there is a caveat at this point, because we do not even know at this point whether the left hand side is non-empty. I told you the fact that the left hand side contains all but finitely many primes of f, but we have not proved it yet. So, a priori the left hand side could just be an empty set, but that is not the case, and we will prove that later in the course, that the left hand side contains all but finitely many primes. Okay, so, today what we are going to do is we are going to see how these how these objects, how this Frobenius element changes when you change your when you have a tower of number field. Okay, so let me do the following. So, theorem, it will extend to the next page as well. So, let f contained in L contained in K be number fields. Right, okay. Okay. K over F Galois with Galois group G K over L will of course also be Galois with Galois group H. Okay, and assume that okay. So, for the first part I do not need to assume that L over F is Galois or H is normal. So, then the first part says that if I take okay, I need to. So, there is F, there is L, there is K, there is P here, there is Q here, and then there is capital P here, right. So, these are P is above small p, Q is above small p, and capital P is above small q, and so that will be the notation here. So, so the decomposition subgroup so what I am going to denote it like this. So, H sub p, this is the decomposition subgroup of H, right. And so, how do I get H sub p? H sub p is equal to G sub p intersected with H. So, that is the claim, this is the notation. Similarly, similarly for inertia and wild inertia. So, let me not write those statements down here, I will write them in the notes properly. And if P is unramified, right, okay. So, then K over L over P, this is equal to K over F over P to the power F prime. And what is F prime? Okay. So, what is F prime? F prime is equal to the degree of K sub Q over K sub P. Okay. So, that is 1, and then what does 2 say? So, in 2 assume that L over F is Galois, this is same as H is normal. Okay. Then there is a map from Galois group, then there is a map from G to G mod H, which is equal to, or isomorphic, but I will write equal to Galois group of L over F. Then image of G sub P in G mod H is decomposition subgroup of Q in G mod H, and similarly for inertia and wild inertia, and the Frobenius element, and image of, sorry, this is a bit tight here, but image of K over F over P in G mod H is the Frobenius for L over F over Q. Okay. So, it has all these natural properties that you would expect. So, to kind of understand what these natural properties are, or to get a feeling about this, that is where I like to use these field diagrams, and so you should think in terms of those. Okay. All right. So, how does one prove this? So, this is what we are going to prove now. So, I'll kind of only sketch the idea of this proof, and then leave the details as exercise to you, because it is not, you have to do this yourself to understand it. It is kind of immediate if you are used to these objects, and so you should get used to these objects by working with them. Okay. So, I want to understand what H intersected G P is, right. So, by the fact that so if sigma belongs to this, then sigma of P is equal to P, right. Hence, sigma belongs to H P. So, it is clear that H intersected G P is contained in H P. Right. Now, on the other hand, if sigma belongs to H P, then of course, sigma belongs to H, because it contains H P, and sigma of P is equal to P. Therefore, sigma belongs to H intersected G P, right. So, H P is equal to H intersected with G P, right. And similarly, you make the same arguments with inertia subgroup and wild inertia subgroup, right. They have properties in terms of how they act on various elements. Now, what about the Frobenius element? So, if I look at, right, Frobenius element has the property that if I look at this to the power f prime and act on alpha, then this is congruent to alpha to the power norm of P to the power f prime modulo P, which is same as saying alpha to the power norm of Q mod P. So, this element K over F over P certainly has the property of the Frobenius element right, and so that is why it is equal to, because Frobenius element is unique, right. So, K over F over P to the F prime, this is K over L to the P, right. Okay. And so, you prove similarly, so that proves 1. So, this proves 1. Now, for 2 we are assuming that L over F is Galois, right, and so I have a map from G to G mod H, and I take I look at what the image of this inside G mod H is, right. So, if sigma belongs to image of G sub P, then I look at what happens to sigma of Q, right. So, let sigma tilde be in GP mapping to sigma. So, I can write this as sigma tilde applied to P intersected with L, right. So, this is P intersected with L, which is Q. So, hence image of GP is contained in the decomposition subgroup of Q, right. Now, conversely, if something is in the decomposition subgroup of Q, we can lift it to an element in G. So, conversely, if, so you can do it in 2 ways, you can just compare their orders, or you can conversely, if sigma belongs to decomposition subgroup of Q, then there exists sigma tilde in G mapping to sigma, and you look at sigma tilde of P, right. You want this to be you want this to be equal to P, right. So, of course, it need not be true. So, this need not be P, but you can change it by an element in H, right. So, exercise, I will leave this as an easy exercise. There exists H in H such that sigma tilde of H of P is equal to P, okay. So, that will prove what you want. You know, it is not true that sigma tilde of P is equal to P in general, or as I said, you can use the order. Now, and maybe you can finish the proof as an exercise as well. So, so what we did today was we defined this Artin map, which is a map from prime ideals that are unramified in the base field to Galois group of K over F, okay. So, this is where we are going to kind of stop our study of algebraic properties of this Galois extensions of number fields. So, we have done so the approach that we are taking is we want to study this Galois group of K over F, but we are going to study it through decomposition subgroups of various primes, and so that is a purely prime by prime study. So, this is what number theorists refer to as local study. So, that is what we want to start doing, and a systematic way of doing that is through the theory of valuations and local fields. So, in the next lecture we are going to start the study of valuations on number fields. We will classify all the valuations, and then we will study completions with respect to each valuation. So, this is what will give us local fields. Thank you.